Alright, hello everyone, and welcome to another week in our pre-calculus algebra curriculum. So I hope that you all had a successful test 1. This week we're going to be looking at module 5 as we enter into week 6. So we're going to start by looking at piecewise-defined functions, and piecewise functions are just functions that are kind of broken into more than one piece, hence why they're called piecewise. So we're going to look and determine the domain and the range of this first function that we have sitting here. Alright, and we're looking at and referencing our function to the right of the screen here. So I see that this function starts, so I'm going to start with my domain. Remember, my domain is from left to right. Okay, in case we've forgotten, I'll just make us a little note that that's from left to right, and that range is from the bottom to the top. So I'm starting, and that is a solid dot. I'm starting at -4, and since it's a solid dot, we remember that we need to have a bracket instead of a parenthesis, and I'm stopping at 0, but I notice that that's an open circle at 0, so that needs a parenthesis. Now I'm stopping it there because there's a hole all the way until we get to 2. Okay, so I'm going to union or bring it together with, and again I'm going to use a parenthesis because that 2 has us an open circle. So I'm going to 2, comma, and it goes all the way to 5, and 5 has a closed circle, so that needs a bracket. So that's my domain. Now in looking at my range, remember my range is from bottom to top. There's not any holes in the range because if I slid this function on top, I've got something covering every piece from all the way down here at -3, which is where I'm going to start. And I'm going to start with a parenthesis for -3 because again it's got a hole in it there. I've got somewhere where I can meet all the way up to 4. Okay, so there's no need for 2 pieces because this will meet everywhere along the way. Before there was this gap in the range. There's no gap in the range. There was a gap in the domain. Oh no, not. Where is my little... Okay. My little scroll wheel is so small you can't see it. Okay, so now we're going to look at the second example. Okay, we're going to make a table of points so that we can graph our function here. So here it says that our function is less than 2 or greater than or equal to 2. There's not going to be any gap in our function since these are covering each other. I've got a less than and a greater than, but it also has an equal to, so that means the function is going to be fully covered whenever we graph that, and we'll see that here in a minute. But I need to fill in this table of values, okay? So let's say that I just want to start with -4. Okay, so let's plug in -4. 3 times -4 is -12. -12 plus 6 is -6. Okay, and then let's say I want to do -3 and -2 as well. Okay, I think that'll work out well for us. And then for this we'll do -2, and then we'll do 0, and then 2 and 4. That way we've done the negative side and the positive side between the two functions, okay? Starting and stopping at the same place. Now again, I'll just rewrite this in case y'all want to know. So we did f of -4 is equal to 3 times -4 plus 6, and that yielded me that -6. So now on this one I would do f of -3, or the function of -3 is 3 times -3 plus 6, again plugging into this first function. 3 times -3 is -9, -9 plus 6 is a -3. Now I'm going to do the same thing. F of -2 is equal to 3 times -2 plus 6. 3 times negative 2 is negative 6. Negative 6 plus 6 is 0. Okay. So you're kind of seeing how that goes. And I guess I'm going to have to write these up here because there's just no room unless I want to write on the graph, and I don't really want to write on the graph. So I'm going to plug into this. So I'm going to have f of negative 2, because we can have negative 2 on this one, alright? So let's go in here, and let's put that in 1/2 times negative 2 over 1 plus 1. Well, that's going to be negative 2 over 2, so it's going to be negative 2 over 2 plus 1, which is just negative 1 plus 1, which is 0. Okay, and this one's kind of more simple, right? Because 1/2 times 0 is just 0, because anything times 0 is 0. So that'll just be 0 plus 1, which is just 1. Now this one will be 2 over 2, but this time it's the same thing as this, except it's not negative, right? So it's going to be positive 2 over 2, which is 1, and 1 plus 1 is 2. Okay, now let's do this last one, and I did those in my mind because we really don't have the room to write them here. So this would be 1/2 times 4 over the 1 plus 1. 4 times 1 is 4, 2 times 1 is 2 plus 1. 4 divided by 2 is 2, 2 plus 1 is 3. So 4 comma 3. Okay, so now we're going to plot this. So I'm going to start at negative 4 and negative 6. Okay, let's change, call it that, negative 4, and down here to negative 6. It's my first point. Okay, and I'm going to give it a little check to remind me that I drew it. Negative 3 and negative 3, down to negative 3. Give it a little check. Negative 2 and 0. Give it a little check. And then on this one, I've also got negative 2 and 0, so we would color that again. That's why there's not going to be a hole in this one. And then we got 0 and 1. We've got 2 and 2. We've got 4 and 3. Okay, so I'm going to connect the dots. I'm not ever the best at this. And then it's much easier to do on a piece of paper with a ruler. So there's our function. Well, the domain appears to just be going on forever and ever, right? So that's negative infinity to infinity, because these are the same values. So we didn't end up with a hole in our function. Okay, so the domain is continuous, yes. Now here comes the fun part where I go over here and try to find the scroll wheel. Okay, we got it. The range is also negative infinity to infinity, because it just keeps going. Now we're going to try to locate that x-intercept, and it appears that what, negative 2 and 0 is where I cross that x-axis, and the y-intercept is at 0 and 1, right? 0 and 1. 0 on the x, but 1 on the y. And that makes sense because we know that an x-intercept always has a 0 for the x value, and that a y-intercept always has a 0 for the x value, right? So if we were to go hold on, my little scroll wheel, down to example 2 here. We're going to be looking to do the same thing. So I'm going to start at negative 5 because this is what its restrictions are on x. So its x values can only be negative 5, negative 4, and negative 3. It can only have those values. Now this is closed circle, right? Because it's got that equal to underneath it. This would be a what? An open circle, because it doesn't have that equal to under it. Okay, I'm going to make my notes there. Now this one can go from -3 to 1, so let's go ahead and do that. -3, -2, -1, 0, and 1 can be its domain, or its x values, okay, which is the same as the domain. Now let's look at this. The -3 can be a closed circle because it's an equal to, but the 1 has to be an open circle because it's not. Okay, and then let's look at the last one. The last one just says that the domain has to be greater than 1. So I'm just going to go 1, 2, 3, 4, and 5. And I would have a closed dot at 1 because it says it can be equal to. And it says greater than, so it's just going to keep going forever. So we would put an arrow on the end of that. Okay, an arrow saying, hey, I stopped at 5 on my table, but really I could go to infinity and beyond. Okay, so now we're just going to plug these in. Well, every output is 3 because there's no x or anything on that one, so it's just 3 across the board. So that one was a little quicker than some of the other ones. Now this one, we do have to do a little bit of that work here, so let's just find me a place. I'm going to do the work for that one over here because I've got some room for it. So I'm going to do f of the quantity f of -3 is equal to -3 plus 1 squared minus 1. F of -3 is equal to -3 plus 1 is what? -2 squared minus 1. -2 squared is what? 4. Minus 1 is what? 3. Okay. And then I'll do one more, and I'm not going to torture you all into having to hear me work through all these. I'll just give you the answers and let you all work those on your own, alright? Because if I work every single one of these out, we'll be here for quite some time. So that'll be -1 squared minus 1. So that'll be 1 minus 1, which is what? 0. Okay? So that's how you go through and do those. Okay, I don't really have the room to do the other 3, so I'm going to go ahead and just go down here and tell you. So you should get -1, then 0, and then 3. Okay? Now let's work out a couple of these, and then we'll of course let you all work the others on your own. So this is going to be -1 plus 5. -1 plus 5 is 4, because it's like saying 5 minus 1. Okay, then let's do f of 2, which is -2 plus 5, which is what? 3. Okay, and then f of 3, which is what? -3 plus 5, which is what? 2. And then you should get 1 and 0. Okay. Now, I need my tables of values in order to graph this. So what I'm going to do is I'm going to look, see, and see. So I'm going to start with my friend over here on the edge. He's at -5 and 3, so I'm going to put me a closed blob. Remember I said that that blob could be closed. Okay, then I've got another point here, and then I said that the -3 and 3 had to be an open circle, so I'm going to go ahead and give that an open circle. But then look at this next one. When I started, it says -3 and 3, but it says closed circle. So now I can close the circle in, okay? Because this one has that same value and it needs a closed circle. Okay, so that's not going to be a hole in our graph after all. So then I've got -2 and 0. I've got -1 and -1. Then I go to 0 and 0. And then I go up to 1 and 3, but 1 and 3 is an open circle as of now. Let me see if I can I, hold on, my mouse went to sleep. Can I just, there we go, put me out the graph. Now this is going to be kind of like this is going to be a parabola, so it's going to be a curve. Okay, I did pretty good. So now we're at 1 and 4. 1 and 4, so that is going to be a hole right there, okay, because I can't color it in because this doesn't say 1 and 3 like it said the same thing here. It doesn't, so it's really going to be a hole there, okay. And then I'm going to have 2 and 3, 3 and 2, 4 and 1, 5 and 0, and I'm going to connect those dots. But remember I said that that's a greater than, right? So it's going to go on for infinity, okay? So there's going to be my picture. It's a little worse for wear, but it's there and it looks like it should with all the stops and starts. So my domain is going to start at where? -5. And it's going to go to infinity. Because if you look, there may be a hole right here, but up above it there's also another dot at 1. Okay, so the hole's not affecting the domain because I'm covered all the way across because these two match up. So the domain is not continuous, okay? Because it's not going on forever. It's kind of going to stop along the way. Now the range would start at where? -1. Well, range would, well, will it start at -1, or, because that might be tricky. We might say, oh, it starts at -1 because that's where the end of my parabola is. But let's remember, what did we say about the last function? That it kept going down forever, okay? So that really means that our range is going to be -infinity, okay? So that, we've got to make sure we're looking at all three pieces before we make a conclusion, okay? Now, where do we stop on the range? We stop at 4. Okay. Now again, that range is filled up because there may be a hole at 3 on this parabola, but there's not on that first function and there's not on that second function, so the range will indeed go on forever. Now let's locate those x-intercepts. I've got one at -2 and 0. I've got one at 0 and 0. And I've got one at 5 and 0. Now where is my y-intercept? I cross the y-axis at 0 and 0. Okay? So we just have to make sure that we're looking at the entire graph and not just part of it, excuse me, when we're analyzing these. Now if we're continuing, the graph represents Sam's distance measured in feet from his dorm room with respect to time elapsed in hours. Okay. So what does the vertical axis represent? The vertical axis would represent what? The distance from his dorm. Okay. So his distance, and if we want to be technical, what's his distance measured in feet? Distance measured in feet from dorm. That's if we want to be technical. And we would just label it. Now, I'm going to label it up here because if I try to write on a slant, we aren't going to be able to read anything. So it's the distance in feet. Okay, and that's for the vertical axis. So let's think about, well, what does the horizontal axis represent? The horizontal axis represents what? Time. And that time is measured in what? The time from 8 a.m. to 12 p.m. If we want to be very technical. The time from 8 a.m. to 12 p.m. So what do the increasing lines represent? So that means what? That Sam's getting further from his dorm, right? So when I see these increasing lines here, or this one increasing line, That means that Sam is getting further from his dorm room, which is what part C is asking. Now part D says, what do the decreasing lines represent? The decreasing lines represent when he's going back toward his dorm, right? So he's getting closer to his dorm with those decreasing lines, okay? What do the horizontal lines in the graph mean? That's where maybe he's in class, right? So his class, let's see, where'd my pen go? So maybe his class is exactly this far from his dorm. So he's gone to class for an hour and he's sitting there in class, he's not moving. Okay. Then maybe after class he's gone to the cafeteria, and the cafeteria is this far from his dorm room, and he's sat down with his friends to eat. Okay, so his distance is constant. He's this far away from his dorm room this entire time eating his dinner, and this entire time in class. Okay, and then here it just represents that he's what? He's back at his dorm room. Okay, he's back at his dorm room starting here. Okay, what does the y-intercept of the graph represent? The y-intercept right here, and I'll draw an arrow to it, that represents where we started it off. He's laying there in his dorm in his bed asleep, ready to start his day. Okay? So what do the x-intercepts on the graph represent? Those represent the times that he's back at his dorm room. Okay? So he's back at his dorm room, he's not left his dorm room. That's what those are representing, because the x-axis is his dorm room. Okay? Now I already kind of sort of created the scenario for letter H of what happened. I said that he got up and went to class, then he walked to the cafeteria and ate something with his friends, and then he went back to the dorm room. Okay? Really, that could be any scenario you want to create, okay? There's not really a wrong scenario, as it were. Okay. Maybe you want to make that he was out at his girlfriend's house or something. Okay. Visiting her dorm, I don't know. You know, make up a funny story or something, okay? So anyway, that's what happened. So now we're going to look at increasing, decreasing, and constant relationships, okay? So a function is increasing on the open interval I in the domain of f if you're going up the entire time, is basically what that's saying. It's just a very fancy symbols. Okay, it's saying that you're increasing over that time interval. A function is decreasing on the interval if the domain, if you're going down. Okay, a function is constant in the domain if you're not moving up or down, you're just kind of making a horizontal line. Okay, so that's basically what that says in fancy symbols. Alright, so you've got relative local extrema. A function f has a relative local maximum if there is an open interval containing a. That's right here. That means that over this time chunk right here, this is the maximum value, is basically what's that saying. So over that little time chunk there that we got in yellow, that's the maximum time for that. The same for the minimum. Over this little yellow interval B, that's the minimum for that point in time. Okay. You can either have a maximum or a minimum. Okay. And we'd call that a maxima, a minima, or an extrema if we want to have some plurals on that. Okay. So now we're going to analyze the graph at R right and see what we have going on. The set of x values where f of x is increasing. Well, it starts at -7, and that's a closed dot, so that doesn't really matter for these. We don't really have to write a bracket. We're just writing where it's increasing, okay? So it's going to be with parentheses for these. Okay, and then to -4, we're increasing. Okay. And then from -4 to -3, we decrease. So if we really wanted to, we could go ahead and write that down for this one. So from -4 to -2, we're decreasing. Okay. And then where is it constant? That's where we've got a horizontal line, and we've got that from -2 to 0. So we can go ahead and write that down too. I just like to do it as I'm drawing on the graph instead of going back and forth. It's ultimately up to you how you want to do that. And then I'm decreasing again from 0 to 1, so I would union that with 0 to 1 as my other places of decrease. Okay. And then from 1 to, what is this, 5? 5 I'm decreasing, so I'd union the increasing, meant increasing, not decreasing, from 1 to 5. Okay. So I just like to do it as I go and fill in the pieces. Okay. If you want to approach it only increasing and then you look at the decreasing and then you look at the constant, you can certainly break it up that way. I just like to trace the graph as I go and jot it down. Okay. Even if you just had a piece of scratch paper and you just jotted it down as you went. That's probably what I would do. But that's how you read that. Okay. Now finding the relative, if my scroller wanted to work, we'd be in business. There we go. So find the relative extrema of the graph. At x equals what? -2. At x equals -2, the function f of x has a relative what? That's a minimum, right? Because it's a lower point, minimum. How do you know that's a minimum? Because it's not up here in the ceiling, so it's got to be a minimum of, and where are we at? -3 when that happens. So between these little imaginary area, between this imaginary area A, if we want to label it like we did during the notes, between that imaginary area, that is a relative minimum. Okay. Or minimum, since it's only one. Okay. Now at 1, we have a what? Well, between this little bit and this little bit, and I don't know, call it B. If making the letters makes it worse for y'all, don't think about it as letters. Just think about it as little blocked off pieces. Okay, I'm just trying to make it match your notes. So that's 1 and -1. Okay, so what is that? That's a maximum, right? Because that's up. That's not a down. That's a, ooh, I'm going up the mountain and then I'm going down the mountain. So that's a maximum. And where did I say that was at? -1. Okay, and then our final one, we'll do that in purple. So let's say I've got another little area I've cordoned off. So at 4 has a relative what? That's down below. It's like I went down and then I'm going back up. Okay, that's a relative minimum of what? Let's go over to the y-axis and find out. -5. Okay. So that's how we find those relative minimums and relative maximums. We kind of think of it as partitions. Do you want to, whether you want to draw the partition on the graph or not is up to you. It does kind of look a little messy once you've drawn those partitions in. So if you don't want to draw the partitions, by all means you don't draw the partitions. Okay, it's whichever is working best for you at the end of the day. Excuse me. So now we're going to analyze the graph of the function. The set of x values where f of x is equal to 0. That's asking me where y is 0. Okay, that's asking me where y is 0. Okay, because remember this would be the same thing as saying y is equal to 0. So it's asking you where these zeros are. Okay, so you're at -4. You're at -1. And you're at 2. Okay? It's asking you where y is 0. Okay? Now this is asking you where y is greater than 0. So where do you see it being greater than 0? well, less than 0, right? Because it's open away. So they're trying to figure out where it says less than 0. I was reading letter C. Okay, it's best to do letter B before we do letter C, isn't it? So we're trying to find the ones that are less than. Okay, so less than, we start at -5 and we go up to -4, and that's all less than. Okay, and then we're going to union that with -1, 2, 2. Okay, where it is less than. Okay, now we can do the greater than that I was wanting to start with. So from -4 to -1, and that should be a parenthesis, not a bracket. There we are. And we're going to union that with 2, 2, 4. Okay? So that's how we would read through those. Alright. And moving right along, if I can find my friend the scroller wheel. We are analyzing the graph of the following function here, okay, and it's a cubic. The domain and the range should be -infinity to infinity, because I see nothing that's restricting it. There's no restrictions listed. You know, those ones we did earlier, there were some restrictions. There's no restrictions listed on this one, and it's not one where I'm dividing or have a fraction, so there's no restrictions in that regard. It doesn't have a square root, so there's none of those restrictions I've got to worry about. So we're just a restrictionless graph. Okay. Now this one, I would say this is a good opportunity to put it in Desmos, really, and I don't have the Desmos open for us, but we can certainly get ourselves there, I would have thought. There we go. And I would use Desmos for this. Okay, so I would put this equals 0.3x to the third power plus 0.2x squared minus 4x plus, well, that's minus 2. Okay, and there's my graph, and I would just copy my graph over to my picture. So the set of x values where f of x is increasing. So it looks to be increasing all the way to what? -2.34. Okay, so you would say negative infinity to -2.34, and it's going to do, it's crazy. And you're going to bring that together, and we're going to look and see where it starts to increase again, and that is down here, let's see, about 1.9. And it's going to increase all the way until what? Infinity. Okay, well, why didn't it? Oh, why didn't it want to? There it goes. Infinity. Okay. Now the set of values where it's decreasing. Well, we said that it started decreasing at what? -2.34. And it stopped at what? 1.90. or 1.9 we said. Okay. And it's, Desmos is going to express that as a point, and it's not. Where x equals 0, is it what? Negative 0.49, negative 3.74, and 3.578. Okay. Where it's below 0, that'd be what? Negative infinity to this value. Negative 49235. And then the set of values where it goes above would be what? 3.75 to negative 49. And then what? 3.58 to infinity. Okay. And your relative maxima would be at negative 2.34. Alright. And then your relative minima would be at 1.89 and negative 6.82. Okay. I think that's the easiest way to look about doing those. Okay, so now let's come back to our worksheet. Let me find my little... The profit of a company is illustrated by the graph shown. Use the graph to estimate the set of years in interval notation for which the profit was increasing. Okay. So I'm looking for increasing. So it looks like it starts at what? From 0 to 1. So from 0 to 1. And then from years 3 to 4. And then from what? Years 7 to year 10, because it increases that entire time. It just starts to increase more steeply from years 9 to 10. Okay, but it's increasing the entire time. Decreasing appears to happen from what? Year 4 to year 7. It was constant between years 1 and 3. Profit was 0. The x-intercepts. At years 6 and years 8. It's t because it's times. It's a times axis. Looks like we're positive from year 0 to year 6. And then what? From years 8 to years 10. And our profit was negative from years what? 6 to 8, right in here. Okay. Now if we scroll down, is the function increasing or decreasing on the interval? Negative 2 to 3. So on the interval of negative 2, on the interval of negative 2 to 3, are we increasing or decreasing? Well, it looks like we went from negative 5 to 25, so we're increasing. And then we're looking on the interval from 0 to 6. Well, we're at 0, and then we're at 0, and everything in between is what? Positive. So we're positive during that interval. We get negative right after that interval. Okay, so that is this week's material on Module 5. It's just on the different aspects of graphs, so that may have went faster than what we've done in the past. As always, I'm available via email if you need any help.